Welcome back to Forge College Chief Engineers. In our last lesson, CPI configuration and state sharing, we tackled the heavy theory behind cross-program invocations. Mapping accounts, how the Solana runtime enforces strict checks, the underlying mechanics of program-derived addresses. Well, today we're taking all that theory and translating it into a tangible, working CPI build. You survived the abstract concepts, which, let's be honest, is usually half the battle when you're programming with Solana. So grab your hard hats. We're going to actually build a minimal, working CPI end-to-end so you can see state sharing in action, and more importantly, do it without accidentally blowing up your local validator. It's going to be hands-on, a little mechanical, and honestly, highly rewarding. Here's the quick blueprint for today's build. We'll set up our workspace schematics, build out the target program, wire up the caller, run a full integration stress test, and of course, debug the inevitable machine recalibrations that pop up along the way. All right, let's dive right into laying the foundation with our blueprint and setup. Every good build starts with a rock-solid workbench. Your workspace really just needs 4 key schematic files to get up and running with Cargo and the standard Solana toolchain. First, you've got your main cargo.toml defining the whole workspace. Then, we've got 2 separate member crates, the target program, which you can think of as the vault holding our state, and the caller program, which is the crew we're sending in to interact with that vault. And finally, the integration test file, our secure test lab, so we don't even need to touch a remote cluster just yet. Moving right along, let's actually build out that target program. We are intentionally keeping this target program super small. It's just a simple mechanism designed to safely mutate state in a straightforward 3-step process. First, we dynamically borrow the mutable account data. Second, we read the first 8 bytes as an unsigned 64-bit integer and we increment it. Third, we write those updated bytes directly back. We're using explicit little-endian byte-level serialization here just to keep exactly what's happening under the hood completely visible to you. No magic tricks. But hold on, here's an absolutely crucial safety check. Before any of those gears turn, the target must assert ownership. It literally has to guarantee that the counter account's owner exactly matches the target program's ID. If you try to mutate an account you don't own, boom, the Solana runtime immediately halts the operation. It's the ultimate safety valve to stop programs from maliciously overwriting each other's state. With a target built and locked down tightly, let's switch gears and start wiring up the caller program. To make the actual invocation, you're going to use the AccountMeta list. Think of this as assembling your electrical wiring. You are telling the runtime exactly which accounts need write access and which are signers. You absolutely have to mark our counter account as writable here using AccountMeta.new. If you flip the signer bit incorrectly, the whole connection is going to short-circuit before it even reaches the target program. And this brings up a really interesting fork in the road for your instructions. Using invoke versus invoke signed. You'll use the standard invoke API for basic interactions, but you switch to invoke signed, passing precise seed slices and bump values when a program-derived address, or PDA, needs to programmatically bolt on a signature. If your target requires a PDA signer and you just use regular invoke, no way. The runtime will reject it outright. All right, the blueprints are drawn, parts are machined, wires are hooked up. Let's fire up the machinery and our local test lab for the integration stress test. Using the Solana program test harness, we are going to deploy both of our compiled crates. We'll initialize a test counter account, fund it with some lamp words so it's rent exempt, and give it 8 0 bytes of data to hold our integer. Then we simply run the caller program's instruction. The absolute beauty of this local environment is that we can inspect this entire state sharing execution without ever having to touch a live network. If your mechanical wiring is flawless, the transaction will complete. Decoding those first 8 bytes will reveal a highly satisfying increment of +1. Seriously, this is the exact moment you get to observe cross-program state sharing actually working in practice. It's a great feeling. But let's be real for a second here. What happens when the gears grind to a halt and sparks start flying? Because, on your first try, they almost always do. You might be staring at your screen wondering, wait, why is the runtime screaming at me? Well, when a CPI fails, it definitely doesn't fail silently. It throws a very specific instruction-level runtime error right in your face. Knowing how to read these logs, that is exactly what separates a novice from a master engineer. So here is your troubleshooting matrix for the big 3 failures you're likely to see. If you get a write access error, well, it usually means you forgot to use AccountMeta.new. If the callee is reading complete garbage data, you probably passed the accounts in the wrong order.
They must match exactly. And if you get a signature privilege escalation error, that PDA mismatch means you either used invoke instead of invoke signed, or your seed arrays are just slightly off.
All right, let's wrap up this build and look at our next steps, because while getting a +1 on a counter is awesome, it's really just the foundation. If you only retain one piece of engineering wisdom from this entire explainer today, literally let it be this golden rule. The account list you assemble in the caller must perfectly mirror the callee's expectations. Ordering, writable flags, signer bits, they are strictly runtime enforced. You have to respect the mirror. As part of the Programming with Solana track, your next steps involve mastering CPI error handling and hardening these setups with CPI security. We really need to learn structured ways to catch these failures and protect against adversarial inputs so our programs don't leak sensitive seeds. Oh, and if you want a stretch task for today, try modifying this exact target program to accept an authority PDA and only allow increments when the caller proves that PDA signed. So, are you ready to engineer a more secure future? To dive into those advanced structures, handle complex failure modes, and find even more blueprints? Head over to forge.college and keep building. This has been a Forge College Explainer. Now that you hold the keys to seamlessly bridge different smart contracts together, what powerful interconnected protocol are you going to build next?